Okay, so today, welcome. And today for this seminar, I will talk about recent works that we did with Philippe and Marceau on multi-agent reinforcement learning. So my topic more broadly is about applying reinforcement learning, not necessarily multi-agent, to design new medium access protocols and for the critical communications application use case. So I will present this to start. Yeah, we start with the context. So as you know, in 5G, a main use case category that was put forth is critical communications among high-speed internet and massive IoT use cases. And more specifically for critical communications, stringent requirements were defined for the latency and reliability of applications. More specifically, let's clear up right now what they meant by latency. So there are two kinds of latency that we commonly talk about in wireless systems. There's the end-to-end latency and the user plane latency. The end-to-end latency encompasses all the steps of communication between the transmitter and receiver. So you have the application processing, all the layers of the stack, transmission over the radio access network, and routing in the core. Whereas the user plane latency only focuses on the radio access network latency. So the time between the moment the packet enters the URLLC layer at the transmitter of the radio access network, so the user equipment, and the time it is decoded at the base station at the same layer. And so for the requirements of URLLC, the kind of latency that we focus on is end-to-end latency. So here I put some of the main applications that are envisioned for 5G. You can see that the end-to-end latency requirements are very stringent. They go as low as 1 millisecond. And for the reliability, the 3GPP has defined the reliability as the probability that a packet is successfully decoded within the end-to-end latency deadline. And so for the reference transport block size that they use for reliability measurement is 32 bytes. So at the introduction of 5G, a lot of efforts were made to enable these use cases. And here I've put some of them, but we won't go through through them all. Specifically, the transmission time interval was greatly reduced from 1 millisecond in LTE to as low as two OFDM symbols in with configurations that we call mini slots. And there were also new numerologies. So there's a flexible numerology. You can have wider subcarrier spaces so that the OFDM symbol time is greatly reduced. And so the end-to-end latency was really, the potential end-to-end latency is really reduced because of that, and it enables URLLC use cases. So here on the right, you can see some measurements that were led in a campaign by the 3GPP at the introduction of release 15. And as you can see, for a low number of users, Here is the factory automation use case. The URLLC was achieved. URLLC performance was achieved. So, one thing that it can be said right away is that a main enabler for URLLC is to do grunt-free scheduling for the layer 2. Grunt-free scheduling is essential because with grunt-based, with even low numbers of users, you cannot achieve URLLC. So after this release, but you can see that there's still progress to make because with 4D UEs, you already have a decrease of performance. And for factory automation use case, for example, a single controller can have up to 100 sensors to control. So you need something more scalable than this. So I won't go in detail for these slides. It's just to show a bit what changes were introduced over the latest releases of 3GPP to further enhance the URLLC capability. So for example, here perhaps the most important for my outlook are the changes brought to the layer 2, since I focus on multiple access strategies. And you can see that they introduced the possibility to have multiple active configured grants. So configured grants is semi-persistent scheduling. So it means periodic allocation. And you can see that they added the possibility to have multiple active configured grants. So it was already an enhancement. Later, in release 17, they further enhanced, but for various at various stages of the layer 1 and also layer 2, with yes, various enhancements that you can see here. For example, here it is described the advanced rate matching features for the encoding of uplink control information. And in release 18, so last year, there were again a few enhancements, mainly for edge coverage. And we're now coming to the upcoming changes that are brought by the 3GPP, and that sort of frame my work, that are really the work that is being done for release 19 and 20 on AI and machine learning based network architecture, network functions architecture at all layers. So not only, for example, for orchestration and slicing capabilities, but also for layer one applications such as channel side information prediction and beam management, because we have to optimize massive MIMO, but also at layer 2. But the thing about layer 2 is that the dynamic scheduling mechanisms are not formalized by the 3GPP. Their policy is to let this design to equipment vendors and companies. So, and they do that in collaboration with academic research, of course. So it leads to my research, which is to design new multiple access schemes and scheduling schemes. And in the line with the enabling 3GPP work, so we have a framework to implement machine learning models in the network. And what we aim to do is to implement reinforcement learning based solutions. So why reinforcement learning? Because reinforcement learning is a really adapted framework for the scheduling and multiple access problem, as we can represent the state of the network. as the state of an environment of a reinforcement learning framework. So the typical one is Markov decision processes. And then the agents take actions on the environment, for example, choosing to transmit, or for example, the choose to schedule. And we get rewards, and our rewards will be shaped to enable the URLLC requirements. Let's see a bit the multiple access schemes categories and to which we can apply reinforcement learning. So right away, as we said earlier, grant-based scheduling is not applicable because it is just too slow to ask for a permission to transmit, then get the permission and transmit from a user equipment perspective. And so it lets us with grant-free schemes. There are two approaches for grant-free. One is to be coordinated by the base station, so have configured grants as before in 5G. And a new envisioned approach would be uncoordinated multiple access. So in uncoordinated multiple access, there are multiple approaches, but one that interests us is modern random access. So what is modern random access? Modern random access is inspired on the random access procedure of serial networks, where we access the network with a slotted ALOA-based procedure. And the change in modern random access is that each UE will transmit multiple packet replicas, and at the base station, these replicas will be received with interference between the users, but they will be decoded with a successive interference cancellation mechanism. So it has already been, of course, considered for throughput maximization. So to have enhanced throughput when a large number of users access the network, so in MMTC cases. But it is actually promising for URLLC. Because the fact that the users are uncoordinated means that they don't need to access the network first. And so it means that we can do a multiple access schemes without scheduling, without effectively scheduling the users. So I present now briefly our approach in the recent works that we did. So our setup was that we consider one cell, KUEs in the cell. They concurrently operate uplink transmissions to the base station. And for our frame structure, so we take a TDD frame structure, and we have some slots reserved for the uplink transmissions. After the uplink transmissions, we have one downlink slot for the feedback given by the base station. So we can have an acknowledgement and other information in the feedback, and it is what will be interesting for our work. And then we have one guard slot for accounting for propagation delay and turnaround times. For our traffic model, we considered aperiodic traffic, so which is more challenging than periodic, with Poisson processes. And we considered to model the URLLC constraints that all the UEs have a strict latency constraint. And so for the arrival of the packets, our arrival of packets is done yes, each UE has a buffer. We suppose unlimited buffer capacity, and that the packets arrive in the buffers, and we have a representation of the buffer statuses of the UEs with a matrix. So this matrix has one line for each UE, and at each column, you have the number of the packets that have the corresponding deadline to the column. So here, for example, this column means that there is one packet for UE1 that has to be transmitted at the next frame. And so the packets move from the left to the right in our representation. Now for the communication procedure, I said that we have a SIG decoding, but let's detail it a bit more. Suppose in this example that the UEs emit copies of their packets to transmit their head of buffer packet. And along with the head of buffer packet, in our model, they also transmit a copy of their buffer status. And so let's say that this is our example. Here you can see that on some slots there are collisions, for example, slot 3 and 4, and on some other slots there is no collision. And I just saw that I did an error on that slide. Sorry, because so here there's no collision on slot 1 and 2, but let's do as if there was a collision. Because what will be done is that the slots that have no collision are decoded and their interference are cancelled on the other slots where it was emitted. It is done at the base station, right? And so iteratively, you can see that other slots end up having no interference, and we can iteratively successively decode multiple users. Okay, so now let's detail a bit what happens once the base station has decoded the messages. After having decoded the messages, the base station feeds back something to the users. It has to feed back acknowledgement, so who was successfully decoded, but we actually use this feedback to bundle more information than the acknowledgement. So we send 2 vectors, so we formalize this as vectors. We have one vector we call the alpha vector. In this vector, there is as many components as there are UEs, and for each UE, it's non-zero if the UE was decoded, so you can see who was decoded or not. And the higher the value of the alpha coefficient is, the higher the UE that was decoded was critical. So it means that, for example, this UE was decoded, but its packet was very critical when it was received. So the alpha value will be higher for UE1, and then it will be same value for UE2 and 3. And so the base station feeds back the alpha vector, and it also feeds back an estimation of the overall traffic, so that yes, each UE only knows its own buffer and an acknowledgement, but it can also acquire information by this feedback on the other UE's traffic. That's the idea. So to do that, we keep an estimation of the buffer matrix at the base station. So here there is the example of this estimation buffer matrix. So we don't put all the definition of this estimation buffer matrix behind here, but the idea is simple: is that every time we successfully decode a packet, the UE has sent its buffer status in the packet. So we can replace the buffer status in our estimation. And we can also know that frame after frame, the buffer status advances to the right. So we have an estimation of the buffers of the traffic, and we can just sum all the lines so that we know for each frame the estimated traffic. And so we feed this to the UEs, and the UEs can figure out what to do next. That's the idea. So now our problem is to the formulation of the problem is just to maximize the URLC capability of our system. And so we formalize this as a score that we call the URLC score. This score is simply defined as the ratio between the number of packets that we successfully decoded and the total number of packets that we sent at all. And so what we will do rather is that we will not only maximize U, but we will also maximize the alpha values, because we know that the more urgent the packets, the more urgent were the packets that we successfully decode, the best it is. As if you have multiple users and the scheduler in the end, here is not a scheduler since it's autonomous, but if it is globally chosen that one UE will be decoded but with a less urgent packet, of course, in the future, it is less it is less probable that we end up with a higher score. So now we had the problem formulation, and now we formalize this into the reinforcement learning framework. We use a multi-agent reinforcement learning framework, which is the DEC-PO-MDP. DEC-PO-MDP is simply a multi-agent generalization of the MDP framework to the partially observable environments. So here, each UE only knows its own buffer status, so it's not observable. And it's decentralized, so we have multiple agents. Our agents are the UEs. One time step of our environment corresponds to one frame. The environment states are taken to be the buffer statuses, so the buffer matrices. And the actions are the slot choices at each frame. So they're defined by vectors that are one where we emitted on the slot. And so the reward that we earn is the number of successfully decoded packets after a given frame, plus the criticality of the packets that were decoded. So as I said, it's partially observable. So each UE only knows B, so it's buffer status, and the last feedback that was sent by the base station. Like and so we define also the internal state of the UE as the history of its past actions and observations, since it is also useful to make the best decisions. And so the policy of the UE, its slot choice behavior, depends on this history. And so in the end, the agents aim to find the policy maximizing the typical performance measure, which is the expected value function starting from a given initial state. So now that we have the formulation, the algorithm, how do we optimize? We use a multi-agent adaptation of PPO. So PPO is a very popular algorithm for single-agent reinforcement learning. It is popular because you have robustness guarantees. And HAPPO, the adaptation that we use, is is uh, is it is very new because the paper was 3 years ago, and it was only very formalized last year. But it is a very interesting algorithm because it considers heterogeneous agents. So you have one policy per agent. So it means that you can have a more optimized behavior. In our case, it means that you have one slot choice behavior per user, so you can have a reduced collision likelihood like this. And so the idea of HAPPO, how it works, is that you have an iterative process of data collection and training phases. So let's go over it, not in so much detail, but let's detail a bit. So in the data collection phases, in our case, it is orchestrated. It has to be orchestrated by someone. In our case, it is the base station. So in the data collection phases, simply the DEC POMDP is executed. So you have a sampling of trajectories. The UEs, according to their policy, do slot choices, and we gather trajectories of the DEC POMDP with the rewards and also the internal states that it can be reconstructed from the action and observations. Then once the data has been collected by the base station, so at the end of during the data collection, the UEs memorize their trajectories, and at the end, they send it to the base station, of course. Once the base station receives all this data, it reconstructs the sequence of encounter states. And then it uses these states to operate sequential update procedures with the UEs. So to update each UE sequentially. Because the problem of multi-agent reinforcement learning is that if everyone updates at the same time, you don't have guarantees to increase performance. Because each UE will maybe go in a direction, but depending on what one UE did, when the other, what one UE did, the other, when it updates its network, the objective function will be flawed. And you have an increasing noise the more the procedure continues among the UEs. So here, HAPPO solves this problem with the sequential update procedure. The base station first samples a permutation of the UEs for the sequential update. Then it computes M coefficients. So the M coefficients are the solutions. The M coefficients are the estimated advantages. So like in PPO. And so here we use the generalized advantage estimator, which is really popular for PPO, where this advantage estimator uses, of course, estimated values of the states that we reconstructed. And it's held at the base station. The base station is orchestrating the training. And then once the M coefficients have been computed at the base station for the first UE, the base station sends to the first UE. The first UE receives the M coefficients. So it receives the advantage estimates. And what it does is that it does a standard PPO, a PPO step. So it uses here, it optimizes with gradient ascent its parameters by using, here we recognize the PPO surrogate objective. So you have the eligibility vectors. you have the advantage estimates and you have the clipping function. And then the difference is that here at the end of, after having updated its parameters, it computes M coefficients for the second UE. And so the coefficients for the next UE are just the M coefficients for the current UE, but multiplied by the updated eligibility vector. So so it means that now now this M coefficient for the second UE, K12, is sent to the base station, and the base station will send it to UE K2, and the K2 will use it in the same way. But it means that when the UE K2 will update its parameters, the advantage estimates will take in account the modification of the parameters of the first UE. So it solves our problem of independent update parameters. And so, as I was saying, here is the update procedure scheme. You have the M coefficients for UEK1 that are received by UEK1. It sends coefficients for UEK2. It is sent to UEK2, parameter update, and then parameters for UEK3, and so on. It goes on until all the UEs are updated. Once all the UEs have been updated, all what is left to do for the base station is to update its own parameters, so the parameters of the critic, to have to keep accurate advantage estimates. And so what we do here is standard. We just do a minimization of the mean squared error between the value function estimate and the rewards to go coefficients. So it's the estimated returns based on the samples. And so for the big picture, you can see here that you have data collection phases, training phase and training phases, and you have an alternating procedure, and you repeat steps of this alternating procedure until convergence. And so one detail that is worth to note is that yes, in our what we did is that we tested our algorithm. So yes, we tested our implementation. We didn't develop the algorithm, but we implemented the algorithm, and so we tested it. Here are some of the parameters, but I just wanted to display that, stress out that we used deep neural network parameterizations, which is common for our UE policies, and the same for the critic. And we used so it is small networks. As you can see, you have 3 MLP layers. And K, that might be small. Okay, and so we compared the performance of UMRA HNPO against 3 baselines. So the first baseline is simply just the unoptimized modern random access. So we just do a uniform degree distribution with so IRSA is just it's just a way to say that each UE has the same probability to emit at each slot. So it's completely random, unoptimized. Then we have round robin. Round robin, in round robin is the same as a standard configured grant scheduling. So you have just a periodical allocation, just like in 5G, in grant-free 5G. And a third baseline, of course, the oracle. So what it will be if you have an optimal allocation where the most urgent packets are scheduled at each frame, which would be ideal. But it will require a shared real knowledge in real time of all the UEs. So it's not possible, of course. Otherwise, the problem is already solved. And so here are the results of our tests. Here in green, it's a bit more small than I expected. But here in the outline, in green, it is the HAPPO solution. In red, it is the random baseline. And in blue, it is the round robin, so periodic allocation. And so first of all, the algorithm, the HPPO converged. We could wait for that. It has been demonstrated, but it converged, and it outperformed the unoptimized version, and also interestingly, it outperformed even the unoptimized version was already outperforming the periodic allocation scheme. And this with an increasing tendency as the number of users increase and as the load of the network increases. One interesting thing that we see is also that with this kind of methods, you see that there is a trade-off to study for the frame size, because if the frame size is too small, you have too much collisions between the UEs, but if it is too high, you only have a small number of retransmissions, possible retransmissions, because when a package is not decoded, it's just retransmitted until it is successfully decoded. So you can see that in practice, a trade-off has to be found for this kind of methods. And so what we plan to do next is to extend this algorithm to more realistic use cases. So here we suppose that when a packet is received without collision, it is automatically successfully decoded. And we did not have really a channel model per se. So we will extend it with a channel model. And it will be the occasion to extend to time frequency resource block allocations. And so we might see an increased performance because we will multiplex in frequency. And so we will have more packet copies transmitted per frame. And so we will also have time varying channels and more real cases studied. It is. Okay, so thank you for your attention. I'll welcome questions.
Hello, thank you for a very good talk. Can you hear me? I mean, I don't know if this is working or is it on? Yeah. Okay. So I have two questions.
Okay.
And the first one is when you're talking about early on, when you're talking about there is a frame where there are 4 slots for uplink and then there is only 1 slot for downlink.
The frame structure.
Yeah, I got the impression that the the feedback from the base station is sent to the UAs for all UAs in the same slot.
Yeah.
But when you are explaining your method of machine learning, algorithm of machine learning,
yeah,
I got the impression that you send the feedback once at a time to the UE.
yeah,
It's not
mm.
everybody simultaneously.
Yeah.
So anyway, I don't know what is exactly the situation, but the question is, how does this thing scale up in number of UEs?
Yes, it is a question that we were asking ourselves, because the thing is that originally what we wanted to do is the alpha vector to be of size of the frame, not the number of users. So it means that we would have, for example, a non-zero value for each slot that was successfully decoded. But it means that at the base station, we have, no, it means that for all UEs, we have a bit less information. Actually, we did not do the tests in the end with this version. We could have, but it is something we thought about.
Okay.
But,
so the second question is, can you show the performance, the results once again?
Yeah.
Yeah. So what is on the x-axis? What is?
It depends. Here is the number of users.
Yeah.
Here it's the load.
Load. What do you mean by load?
Packets per second.
I see. Okay.
And here is the frame size, the trade-off.
On the x-axis?
Yeah.
Okay. So the question is basically, I mean, when you are talking about, and you said that early on, when you are talking about low latency, it is better to have a very frame size and very small slot size. And that means a rather wide carrier spacing, subcarrier spacing. And usually, I mean, all these things are for IoT applications.
Yeah.
And the sensors have only a small amount of data to send. So if you take a small slot, that means a very large carrier bandwidth. So you are wasting bandwidth. And this also, you show that there is an optimum on the frame size. So, I mean, how all these things interact together?
So it will be part of our future work because here the thing is that we could not test it because we don't have a channel model. We only have in time. We don't model what's going on in the frequency. But what we might see is that depending on the subcarrier spacing, you may have more or less blocks, but a smaller slot, and a trade-off has to be found for this also, and also for the actual decoding probability.
Okay.
Yeah. Also.
Okay. Thank you.
Just to continue on this picture question, you will have to cram the kind of buffer, 3D buffer into the feedback channel also, like if you had before a problem to encode the buffer status and push it down as a feedback from the base station when you get multiple subcarriers. So basically this sort of, how big will that be and whether it will fit within?
Where we don't expect to. We don't expect a single subcarrier to contain a transport block. Of course, we will
have to send it on all the subcarriers for each subcarrier.
Not all the subcarriers, but maybe we will have a slicing. Like we'll have slices in the subcarrier space, and we will have multiple transport blocks in the frequency domain 4. But we will keep one slot. it will be one slot times a given number of subcarriers is one block. And so we have a varying number of blocks depending on subcarrier spacing and a varying number of time slots in the same time. And it will be non-trivial because depending on the channel, maybe you will have a given coherency bandwidth. So it is non-trivial to know. It's not the same to reduce or to widen the subcarrier spacing.
Yeah, I had another question. Among your baselines, you do not include the proportional fair. Is there like a reason why? Like because probably it's memoryless. I think you use a Poisson model for traffic.
Not think about it, but
yeah, I mean,
for suggestion.
Yeah, I was wondering because most schedulers try to apply that, and so it's a realistic case which may be of interest.
Yeah, might look into it. Thank you.
Thank you.
Thank you.
There are no other questions. I have 3 questions, very quick.
Oh, yeah.
So if you go back on slide 29, it's the previous one, I think. So quick question number 1, the time slots for training. I may have skipped that information. How much actual time they correspond to? Do you know, or is it just a number identifying the step?
You mean
in the x-axis it's written total number of training time steps.
Yes.
So does it correspond to what amount of time of exact time? Do you have this information or not?
Of simulation time.
Simulation time. It's not real. Okay. Not real time.
Yeah, and actually, it's kind of a bit long for now, but it's more a matter of code optimization.
And for all this amount of time, the number of UEs were constant.
Yes.
So which means, do you plan to integrate what happens if a new UE enters?
We thought about it, and the thing is that it's actually we so the big picture that we were thinking about at the beginning was a global system. So we have multiple UEs, and perhaps we could be in the cell-free MIMO environment because it will be maybe more efficient. And so the issue that we will have is that maybe one UE, yes, it will depend on the mobility pattern of the UE. And the thing is that it will have to be there will have to be some centralization of the feedback. There will have to be some homogeneity of the feedback along the training.
Because the question in simple terms is, do you need a full retraining or not when a new UE enters?
Full retraining or not? Oh, you mean when the UE enters in the current state? It has to be studied because maybe we might study transfer learning. So have a base, maybe train a base configuration, and then give it to a new UE that comes. It's a good
and the last question is, okay, you talked about the mobility pattern, so maybe you want to take into account also the mobility of UEs.
Yes, for now for now we just focus on extending to a real case with the time frequency domain.
Yes, sure.
But yes, in the end goal, yeah.
And my question was still in the training phase, so the time steps that you were showing on 29, on slide 29. I was wondering, I'm not sure it is visible here. Have you seen the number of UEs impacting your training, both in performance or in quality?
Yes, actually here, these curves it is just the Y is not a loss, it's just the raw performance.
Yeah,
So,
but because actually you are using, I don't know, 500,000 times step, etc., to reach that point,
Yeah.
a point that is maximum in your scenario. My question is more about the fact of having 2 UEs or 10 UEs impacting how long you will take to reach that point?
How long? Yes, actually, yes. Good
Because
question.
that's also interesting to show.
Yes.
It proves
That's true.
the scalability or not of your algorithm.
Yes. But let's say that yes, here we took a very long training, and we assume that it will be, yes, of course. Here it was for 10 users, so you can see that the results here in the curve go up to 10 users. For 12, it's approximately the same curve. And for all the other users, it will just be a bit sooner, always a bit sooner. So,
because that also reflects how many UEs are you willing to accept in your calculations? Because maybe you can
depending on the time I have to train them. Yeah. Yes.
Yeah, that's okay.
Yeah.
This clarifies my
Okay.
doubt.
Yeah. But yes, it was maybe I could give you a bit of an idea. Maybe for 2 users, maybe here you already have had the optimal.
There are no other questions. Maybe we can thank again the speaker. Thank you.
Oh, yeah. Thank you.
Do we have Fritz? You're invited to join us for some.
Of course.
Viennoiserie. C'est quoi, c'est viennoiserie?
Yeah.
Madeleine.
Ah, il n'avait plus. D'accord. C'est Madeleine. C'est pas sur côté.
C'est ceux-là, mais je vais le changer.
Moi, je compte.
Voilà.
Mais bon, les fautes, pour les moi, les résultats, là, tu vois vraiment dire vraiment ce qu'il y a sur la biologie.
Ouais, j'ai pas dit les fax.
D'abord, faire des remarques. Idiote, quand tu dis que c'est comme ça. Puis après, alors je sais que c'est pas important. Et après, insister sur un plus étonnant, etc. Mais il faut vraiment dire qu'il faut être un peu plus élémentaire sur les figures, faire un pour dès que tu vois des courbes, en fait, elles paraissent tout du coup.